Okay, so let's talk about this HSW theorem. The idea is that you want to know how many bits of information by second we can send without making errors going through a quantum channel. So, for example, if your classical capacity is of 2 bits, it just means that if you just send a lot of quantum packets, you can reconstruct the message of Alice from Bob with a rate of 2 bits for each sending without any error of interpretation. And so the formula of all the rules tell you that if the quantum canal, if you have the quantum canal, you might send untangled collections of information. So to be able to have the maximum out of the canal you want to have. So instead of created really hard, complicated coding, I'll just generate a dictionary, using probability laws. So that's what we saw, in the last course about entropies. It's just like if you take your piece, like, and you send it for example 1,000 times. So money, you have money. It will be either on one face or in the other face. Say one face is white, the other face is black. And so if the face is white 1,000 times, then you can understand that there is a problem about it. And so it's not living in the typical subspace because most of the time it will be 500 time, 500 time, not 1,000 time black, but 5,000 time black, 5,000 time white. Because that's how it works. So yeah, she just like take a piece and sending 1,000 time, a lot of time, and take a dictionary about it, and after she just threw away the 1,000 black or the 1,000 white and just keeps a typical subspace where it is a normal amount of, uh, of black and white. So let's say like the piece has normally 70 per, if it is like a tricked piece, the piece do not have like 50%, but 70% to be on black and 30% to be on the white. Then you will have like, so most of them will be like 700 black and 300 white. And so yeah, if 1,000 black or 1,000 white, we eliminate them because it's too atypical. Yeah, we just take the sequence into our error window. So we can after translate the password, the classical password, into quantum state and sending them through quantum optical fiber. So let's suppose that our passwords like black, white, black, the Alice password. And so she just prepares 3 photons into the polarization corresponding. So let's say like it will be vertical for black and it will be horizontal for white. The quantum canal, like just sends those 3 photons to Bob, but with a little of perturbations. That's the principle of a channel. And so Bob just receive psigs are black, psigs are white, and psi are black using this. And so we have this, and what Bob receive, um, he will know like for a certain x, that's y, I will be less or more into a group of probabilistic results, because like the channel will always like to transform the noise into a into a certain way, and so it will be less or more the same deviation. So typically, if Alice is sending like black, um, Bob can receive like white with only 10% and black with 90%, And so it means like 900 on 1000 time it will be still be black, so it works most of the time. And so the signals associated to the word of Alice is called conditional typicality, So let's say maybe it's like say two by the way, because it's a code word that's the way. So yeah, most of the time it will be two, for example. And so to do this, to less pass uniquely the state which is two and not be mistaken, like we construct a projector based on the typical conditional subspace of this Alice working like 900 on 1000 time. But yeah, so as we see before, like the total amount of possibilities, like y to the power of n, each word of Alice is just like 2 to the power of n of h of y, like x. And so if the space of reception of Bob is a big stuff with 1000 Ks, each password of Alice produce a result that it will be going into 10 specific cases. Like let's say that's 10 specific cases, and here's like 1001. And so the probability that it goes here is like 99%, because here is like, so it's like transformers 300 staff and 700 staff, 30%, 70% we're talking about, and here is all the other combination. And so it can represent like 10 cases in reality, and we'll never go over it. And so, for example, because Alice just occupied 10 cases on 1000, like Bob can be able to store 100 password at the maximum, because like we say, like for example we have 10 cases here, and so each of them occupy like 10 stuff, so there will be 1000 person. But like for example, if it goes into the if it will be not judging crossing one each other, Bob can just check where the often arrives. For example, here after the time, and let's say like it's like the box number Karen 42. He will know that the message of Alice will be 42. So yeah, the quantum canal, the capacity of the quantum canal is a maximum of little boxes that we can put into the space of reception of Bob, thanks to collective joint measurements. So yeah, now I have space, typical space, and what are the how many stuff we can put into it, and from here deduce the code words. That's the main point.